Another type of sequence that we're going to talk about is a geometric sequence. The arithmetic sequences, there's a common difference that's added to each term, and we'll see in geometric sequences, there's a common ratio that's multiplied by each term. So in a geometric sequence, we start with a number a, just like always, just like all the other sequences, and then we repeatedly multiply by a fixed non-zero constant. Instead of calling it d like in the arithmetic sequence, for common difference, we're going to call it r because it's a ratio. So the number r is the common ratio because the ratio of any two consecutive terms of the sequence is r. So here's what the nth term of any geometric sequence looks like. The first term is a, the second term is a times r, the second term is a times r, or r squared, and so each consecutive term is multiplied again by that common ratio r. The nth term, the formula for the nth term or any term in this sequence is a, the first term, times r, the common ratio, to the n minus 1. So if we're looking for the 12th term, a sub 12 equals a times r to the 12 minus 1, or to the 11th. So it's very easy to find any term in this sequence. So make sure this formula is written down in your notes and that you understand now we are multiplying each consecutive term by that common ratio r. If we're given the terms in a sequence, we can divide one term by a term immediately on its left, and we can find what the value of the common ratio is, and then we can look to see what the first term is, and that's all we need to know. We need to know a and r, and we can generate any term in the sequence. So if a is 3 and r is 2, then we have this geometric sequence. The first term is always a, so you can see here the first term is 3. The next term is 3 times r, or 2 to the 1. The third term, 3 times r squared, 3 times r times r, 3 times r cubed, and so forth. We could find any term in this sequence because we know what the nth term looks like. So when we clean this up, this sequence would look like 3, 6, 12, 24, 48, and so on. So the common ratio here is 2. We could write the nth term. Remember, a sub n is a. We see that a is 3. Times r, we know that r is 2. We can see that that's r squared, r cubed, r to the 4th, and it's raised to the n minus 1. So if we want any term in this sequence, if we know the nth term, it's just a matter of plugging that value in for n and finding that particular term in the sequence. So here's the sequence: 2, negative 10, 50, negative 250, positive 1250. The first thing I see is that I have alternating signs. The first sign is positive, the second sign is negative, so we'll have to handle that. It is a geometric sequence that I can very clearly see. A is 2, and they tell me r is negative 5, but let's look at how we could find r. We take any term and divide it by the term just to the left. So negative 10 divided by 2 is negative r. 50 divided by, is negative 5. 50 divided by negative 10, negative 5. So it is true that the common ratio for this sequence is negative 5. And if we were to write the nth term, it would be a, which is 2, always the first term, times r to the n minus 1. So it's very easy in geometric sequences to find a and to find r. A is always given to you. It's always the first term. So if they give you the sequence, you know a. You can find r by taking the second term and dividing by the first, or the third term and dividing by the second, and that's going to give you the value of r. If you know a and r and you know the formula for a geometric sequence, you can always find that nth term. So here the nth term for this particular sequence is 1. We usually don't write 1 times, but it's shown here so you can see that it is in there. And it's 1/3, because that's r, to the n minus 1. So we can find the nth term of a geometric sequence if we know any two terms. We just take the second term divided by the first term, or the third term divided by the second term. We take the right term and divide it by the term just to its left. That gives us the common ratio, and then the first term is always a. So here we can clearly see that a is 5, and if we take 15 and divide by 5, that's 3. We could also take 45 and divide by 15, that's also 3. So we can see the common ratio is 3. Therefore, the nth term would be a to the n equals 5 times 3 to the n minus 1. So the eighth term that they ask us for is when n equals 8. So we just substitute everywhere in the formula for this particular geometric sequence. Anytime we see n for the eighth term, we're going to substitute in 8. So that's 5 times 3 to the 7th. We can get our calculator, that's 10,935. There are also partial sums for geometric sequences. There was a formula for partial sums of arithmetic sequences. We're also going to see that when we start to add these geometric sequences together, because remember that's all a series is a sum of a sequence. We still have a, we still have r, everything's all involved. We still have that nth term. And so here's the formula for the nth partial sum of a geometric sequence. So if we want a partial sum of some geometric sequence that we're working with, we still need to know a, we still need to know r, and we just plug it into this formula. So make sure this is in your notes, and if you're asked for the 12th partial sum, that would be where n equals 12, and you would just plug 12 in everywhere that there's an n here. You'll have to identify a, you'll have to identify r, but once you have that, you can find that nth partial sum. So find the sum for the first 5 terms of this geometric sequence. Well, the first thing I need is a. I can clearly see that a is 1. The next thing I need is r. So I take the second term and divide it by the first term. 0.7 divided by 1 is 0.7. So r is 0.7. So I know a and I know r, and so I can find the sum of the first 5 terms. That's s sub 5. So I'm going to substitute that into the formula. A is 1, r is 0.7, and n is 5. And so I plug that in and I get a value of 2.7731. So it's just a matter of knowing the formula if you want to generate or the formula for a geometric sequence if you want to generate the sequence. Given the sequence, it's a matter of understanding that each term is multiplied by r after the first term. And if you want a partial sum, you just need to know that formula and substitute that value in. The fifth partial sum tells us that n equals 5. So very straightforward. Now, everything that we've worked with so far as our sequences are concerned, has been called an explicit formula. You're explicitly given A, we found D or are given D in our arithmetic sequences, we found R or we're given R in our geometric sequences, but there's also another type of formula that generates the same sequence, but it's called a recursive formula. And a recursive formula is interesting because it's not so much directly based on n, it's more based on knowing a prior term in your sequence. So let's look at what I'm talking about. In particular, for a geometric sequence, the explicit formula was the nth term, a sub n, was the first term times that common ratio raised to the n minus 1. There's the explicit formula we've been working with. Now, instead of capital A, we used little a, but it doesn't matter. And so this finds a specific term, the nth term. The recursive formula is that the nth term is based on the prior term. That's what this notation means. If a sub n is the current term, then a sub n minus 1 is the prior term. It's the previous term to a sub n, and we're going to multiply that by the common ratio. So this uses previous terms to find the next term. If I wanted the fifth term, then that's going to be a sub 5 equals a sub 4 times the common ratio. If I want the 13th term, a sub 13 equals a sub 12, or the term, the previous term, times the common ratio. So if we don't know what a sub 1 is, but we do have a few terms in the sequence, we could use the recursive formula to generate the sequence. So this says create the recursive formula that defines the sequence 2, 8, 32, 128. Well, we could very easily here find the explicit formula, but we want the recursive formula. So what we're going to do is we're going to find R. The first step is the same. We're going to take any term and multiply it by the term just to the left of it, and that's going to give us our common ratio. And so if we want to know what the recursive formula is, it's a sub n equals a sub n minus 1 times r, and we found that r was 4. So we substitute that in here. So let's use this recursive formula to check to see if it works for this sequence. So let's look at the term 32. A sub n, let's say n was 3. So the third term, 32, equals the second term, that's a sub 3 minus 1, or a sub 2, that's 8. So I've written that here, times the common ratio, 4. And sure enough, 32 does equal 8 times 4. So recursive formulas are pretty straightforward too, and they're handy when you might not necessarily know that first term a. So there we are. There's geometric sequences and geometric partial sums. Come to class next time and we'll practice on some homework problems.